What if the universe isn't just a vast, chaotic expanse of isolated stars and galaxies? What if everything, from the smallest atom to the largest supercluster, is secretly woven together by invisible threads? Picture this, a cosmic web connecting all things, where the flutter of a butterfly's wings on Earth might ripple through the fabric of space-time itself. It sounds like science fiction, but what if it's science fact? Behind the veil of the visible universe, there could be hidden connections shaping reality in ways we're only beginning to understand. This isn't just wild speculation. Some of the brightest minds in physics, cosmology, and philosophy have spent lifetimes chasing these very ideas, uncovering clues that challenge everything we think we know about existence. Today, we're diving deep into 30 mind-bending theories that suggest the universe is far more interconnected than we ever imagined. From ancient mystical beliefs to cutting-edge quantum experiments, these ideas bridge the gap between the known and the unknown, pointing to a reality where separation might just be an illusion. Imagine a cosmic symphony where black holes hum in harmony with distant quasars, where dark matter whispers secrets to the atoms in your body, and where the very laws of physics might be different in ways that tie us all together. Sound unbelievable? That's the thrill of exploration, because the more we learn, the stranger and more wonderful the universe becomes. So why does this matter to you? Because these hidden connections could hold the key to some of the greatest mysteries of our time. The nature of consciousness, the origin of life, even the fate of the cosmos itself. This isn't just about distant stars or abstract equations. It's about the fabric of reality and our place within it. Whether you're a curious skeptic or a devoted stargazer, this journey will stretch your imagination, challenge your assumptions, and maybe, just maybe, change how you see the universe forever. Buckle up, because we're about to explore theories so profound, they might just rewrite the story of everything. Let's start with one of the most baffling phenomena in modern physics: quantum entanglement. Imagine two particles born from the same event, spinning in perfect sync even when separated by billions of light years. Change the spin of one, and its partner instantly mirrors that change, as if no distance exists between them. Einstein famously called this spooky action at a distance, because it defies the cosmic speed limit, the speed of light. How can information travel instantaneously across the universe? It's as if the particles share a hidden language, whispering to each other faster than light should allow. But here's where it gets even stranger. Entanglement isn't just a laboratory curiosity. Some scientists believe it could be the universe's silent scaffolding, a web of invisible connections tying everything together. Picture the cosmos as a vast, shimmering network where every star, every planet, even every atom might be linked through this quantum conversation. If that's true, then separation, the idea that objects are truly independent, might be an illusion. The universe could be more like a single, intricate tapestry, with entanglement as the thread weaving it into one cohesive whole. Think of it like this: if you pluck a guitar string in Tokyo, the vibration resonates through the entire instrument. Now scale that up to cosmic proportions. A supernova exploding in a distant galaxy might send subtle ripples through the entangled fabric of space, influencing matter light years away without any detectable signal in between. This isn't just poetic speculation. Researchers are already exploring how entanglement could explain everything from the uniformity of the early universe to the mysterious behavior of black holes. So what does this mean for us? If entanglement truly connects the cosmos, then every action, no matter how small, could ripple through the universe in ways we can't yet measure. Your thoughts, your choices, even the beat of your heart might resonate within this grand quantum symphony. It's a humbling idea, one that blurs the line between observer and participant, suggesting we're not just living in the universe but actively woven into its very fabric. The next time you look up at the night sky, remember, those distant stars might be more intimately tied to you than science has yet dared to dream. Now let's stretch your perception of reality even further. What if the three-dimensional world we experience is nothing more than an illusion, a cosmic mirage projected from a two-dimensional surface at the very edge of the universe? This isn't the plot of a sci-fi movie. It's the radical theory known as the holographic principle, and it suggests that everything we see, touch, and feel might be encoded on a distant, flat boundary like a hologram. The idea was born from an unexpected source, black holes. When physicist Leonard Susskind and others wrestled with the black hole information paradox, the puzzle of what happens to information swallowed by these cosmic voids, they stumbled onto something astonishing. Black holes seem to destroy information, but quantum mechanics insists information can never be lost. The solution: maybe the information isn't gone, it's just smeared across the event horizon, the black hole's two-dimensional surface, like data etched onto a celestial DVD. If that's true for black holes, could the entire universe operate the same way? Picture reality as a giant cosmic theater, where the stage isn't the three-dimensional world around us but a vast, flat screen at the edge of existence. Every star, every galaxy, even your own thoughts, might just be projections from this hidden surface, like shadows dancing on a cave wall. It's as if the universe is running a monumental simulation, with all the complexity of 3D space emerging from a simpler, lower-dimensional code. Think of it like watching a movie. The images appear to have depth and movement, but they're all generated from flat, unmoving pixels on a screen. In the same way, our 3D world could be a kind of optical trick, with the true source code of reality written in 2 dimensions. This isn't just philosophical musing. Mathematically, the equations work. The holographic principle has become a serious framework in theoretical physics, even influencing how scientists study everything from quantum gravity to the birth of the cosmos. What's truly mind-bending is what this implies about connection. If everything in our universe is encoded on a shared 2D surface, then separation is an illusion. Every particle, every force is fundamentally linked by this underlying layer. A change in one corner of the cosmos could ripple through the entire hologram, instantly influencing the rest. It's a vision of reality where distance and individuality might dissolve into a deeper, unified fabric. So the next time you feel small under the night sky, remember, you might not just be looking at the universe, you could be staring at its hidden blueprint. What if the same patterns keep repeating across the universe, from the smallest quantum scales to the largest cosmic structures? There's a strange similarity between the branching veins of a leaf, the tangled web of neurons in your brain, and the vast filamentary structures connecting galaxies across the cosmos. This isn't coincidence. It might be evidence of a deeper fractal order woven into the fabric of reality. Fractals, those infinitely repeating geometric patterns where tiny parts mirror the whole, appear everywhere once you start looking. Zoom into a flake of snow and you'll find miniature versions of its overall shape. Examine the branching of a river delta and you'll see the same twists and turns whether you're viewing it from space or up close. Now look at the universe itself. The Sloan Great Wall, one of the largest known cosmic structures, stretches over 1 billion light-years in filaments and voids, uncannily resembling the neural networks firing inside your skull. Even more astonishing is quantum foam, the seething, chaotic foundation of spacetime at the smallest scales. Here, particles blink in and out of existence in patterns that, when magnified, look eerily similar to the clustering of galaxies. Could these parallels be random, or is there an underlying logic to how reality organizes itself, a hidden blueprint that repeats across dimensions? Some scientists suggest that fractal geometry isn't just a curiosity. It might be a fundamental language of the cosmos, a way for nature to build complexity from simple, repeating rules. Think of it like a cosmic fingerprint. Just as your unique swirls and loops appear at different scales, from the ridges on your fingertip to the larger patterns of your palm, the universe might express itself through these nested designs. Galaxies clump into clusters, which themselves form superclusters along vast filaments, all echoing the branching networks of lightning or the veins in a leaf. Even time might follow fractal rhythms, with cycles within cycles, day and night, seasons, geological epochs, each nested like Russian dolls. What does this mean for our place in the universe? If fractal patterns truly bind everything from atoms to galaxy clusters, then we're not just observers of these designs, we're made of them. Your brain's neural pathways might be a microscopic echo of the cosmic web, suggesting that the universe isn't just around us, it's within us, a reflection of the same patterns playing out at every scale. The next time you gaze at a tree's branches or a crack in the pavement, consider this. You might be glimpsing a fragment of the universe's hidden code, written in the language of fractals. Hidden beneath the visible universe, an immense cosmic skeleton stretches across the darkness, a sprawling network of dark matter filaments, invisible threads weaving galaxies together like beads on a string. This is the universe's hidden architecture, a scaffolding so vast it defies comprehension. Astronomers call it the cosmic web, and it's made of something we can't see, touch, or even directly detect. Dark matter, the mysterious substance that outweighs ordinary matter 5 to 1. Picture an iceberg where the part above water represents every star, planet, and nebula we've ever observed, while beneath the surface lies an unfathomably larger structure, unseen but holding everything together. These filaments aren't just passive ropes dangling in space. They're dynamic highways, channels of gravitational influence that guide galaxies into clusters and superclusters. Computer simulations reveal a breathtaking dance. As dark matter flows along these threads, it pulls ordinary matter with it, sculpting the universe into the intricate patterns we see today. But here's the tantalizing possibility. What if this web isn't just shaping galaxies? What if it's also carrying signals, vibrations, or even some form of cosmic communication we don't yet understand? Consider how mycelium networks operate in forests. Beneath the soil, fungal threads connect trees over vast distances, allowing them to share nutrients and warnings. Could dark matter filaments function similarly on a galactic scale? Some theorists speculate that perturbations in the web ripples caused by colliding galaxy clusters or merging black holes might propagate in ways that subtly influence distant regions of space. Just as plucking a spider's web sends vibrations to its edges, events in one part of the cosmic web might resonate elsewhere, invisible to our telescopes but potentially detectable through their gravitational echoes. Even more intriguing is the idea that dark matter might interact with itself in ways we can't yet measure. While it famously ignores light and ordinary matter, could it have its own dark forces or particles transmitting information along these filaments? Experiments like the Large Hadron Collider are hunting for hypothetical dark photons, carriers of a potential hidden force that might mediate interactions within this shadowy network. If they exist, the cosmic web could be buzzing with activity, a bustling exchange of signals we're only beginning to imagine. Think of the implications. If dark matter's web facilitates some form of cosmic conversation, then galaxies might not be isolated islands but nodes in a vast, whispering network. Supermassive black holes at their centers could act like relay stations, amplifying and redirecting these invisible messages across billions of light years. It's a humbling thought. While we're busy decoding radio waves and light, an entire layer of universal communication might be humming just beyond our perception. The next great leap in astronomy might not be a bigger telescope, but a way to listen to the dark. Butterflies might seem insignificant in the grand scheme of things, until you consider how the delicate flap of their wings could theoretically set off a chain reaction, altering weather patterns across the globe. Now take that same principle and multiply it by the size of the universe. What if quantum fluctuations, those tiny, random tremors in the fabric of reality, didn't just fade into obscurity but echoed across cosmic time and space, sculpting the largest structures we see today. This is the butterfly effect unleashed on universal scales, where the tiniest ripples during the universe's explosive infancy might have dictated the placement of galaxies billions of years later. During the first fractions of a second after the Big Bang, the universe underwent a period of hyper-expansion called inflation. Space stretched faster than light itself, magnifying quantum fluctuations, subatomic blips that would have been negligible under normal circumstances into imprints across the cosmos. Imagine blowing up a balloon with microscopic bumps on its surface. As it inflates, those tiny imperfections stretch into vast mountain ranges. In the same way, those early quantum jitters were frozen into the fabric of spacetime, becoming the seeds for all future structure. Here's where it gets extraordinary. Those random quantum fluctuations didn't just fade into background noise, they became the blueprint for everything. Regions with slightly denser fluctuations pulled in more matter through gravity, eventually growing into galaxy clusters, while less dense areas became the cosmic voids we see today. Your existence, the Earth, even the Milky Way's position in space, might trace back to these infinitesimal tremors in the first moments of time. It's as if the universe rolled quantum dice at its birth, and the outcome determined where every star and planet would form billions of years later. But could these connections go even deeper? Some theorists propose that quantum entanglement, the same phenomenon linking particles across vast distances, might have woven these fluctuations into a coordinated pattern during inflation. If true, then the universe's large-scale structure isn't just the result of random chaos, but an intricate tapestry where distant galaxies are subtly linked by their shared quantum origins. A supernova's explosion in one corner of the cosmos might owe its timing to a fluctuation that also influenced a galaxy cluster halfway across the observable universe. Think of it like a cosmic game of telephone, where whispers from the universe's first moments still reverberate today. The spiral arms of a distant galaxy, the branching filaments of the cosmic web, even the distribution of dark matter, all might carry echoes of those initial quantum whispers. This isn't just a story about the past, it's a reminder that the universe operates on scales both unimaginably vast and infinitesimally small, where the tiniest events can cascade into consequences that shape reality itself. The next time you gaze at the night sky, remember, the stars you see might owe their positions to quantum ripples so small they'd make a butterfly's wings feel like a hurricane. Black holes aren't just cosmic vacuum cleaners, they might be the universe's most sophisticated information storage devices. At first glance, these gravitational monsters seem to destroy everything they consume, crushing matter into oblivion beyond their event horizons. But what if nothing truly disappears? The black hole information paradox, one of the most heated debates in modern physics, suggests that every atom, every particle, even the faintest whisper of light swallowed by a black hole, could leave an indelible imprint on its surface, like data encoded on the world's most extreme hard drive. Stephen Hawking rocked the scientific world when he proposed that black holes aren't entirely black, they slowly leak energy in the form of Hawking radiation, a faint glow of particles escaping their gravitational grip. At first, this seemed to spell doom for information preservation. If a black hole evaporates over eons, radiating away its mass, what happens to all the information it consumed? Quantum mechanics insists information can never be truly lost, yet black holes appeared to violate this sacred rule. The paradox left physicists at a crossroads. Either our understanding of quantum laws was flawed, or black holes were hiding something extraordinary. The breakthrough came with a startling realization: the information might not vanish at all. It could be smeared across the black hole's event horizon, the point of no return, like a holographic projection. Imagine tossing a book into a fire. The pages burn, but the words aren't truly gone. Their information lingers in the precise arrangement of ash and smoke. Similarly, as matter falls into a black hole, its quantum information could be transcribed onto the event horizon's surface in minuscule, scrambled bits. Over time, this data might slowly re-emerge, woven into the fabric of Hawking radiation itself. It's as if the black hole isn't a dead end, but a cosmic translator, converting matter into a new form of quantum code. This isn't just about black holes, it's a clue to how the universe might preserve connections across time and space. If information is never destroyed, only transformed, then every particle that ever crossed a black hole's threshold remains entangled with the cosmos in ways we're just beginning to decipher. Picture a star collapsing into a black hole billions of years ago. Its atoms, now stretched into strings of quantum data on the event horizon, could still be whispering to the universe through Hawking radiation, their influence subtly woven into the fabric of reality. The implications ripple even further. If black holes encode information holographically, could the entire universe operate the same way? Some theorists speculate that reality itself might function like a colossal black hole event horizon, with every event, every interaction, imprinted on some distant boundary we can't yet perceive. It's a dizzying thought that the history of the cosmos, from the birth of galaxies to the flutter of a butterfly's wings, might be preserved in a vast cosmic ledger, forever linking past, present, and future. So next time you hear about a black hole devouring a star, remember, nothing in the universe truly disappears. It simply transforms, reminding us that even in the darkest corners of space, connection endures. What if the universe doesn't exist independently of us? What if it only takes shape because we're here to observe it? This radical idea lies at the heart of biocentrism, a theory proposed by scientist Robert Lanza that flips our understanding of reality on its head. Instead of consciousness emerging from the physical world, Lanza suggests the opposite. Consciousness is the foundation, the cosmic architect shaping everything from atoms to galaxies. It's a perspective that merges quantum physics with philosophy, implying that the universe isn't just out there. It's a collaborative projection, a dance between observer and observed. The double-slit experiment, one of quantum mechanics' most baffling demonstrations, offers startling evidence for this claim. When particles like electrons are fired at a barrier with two slits, they behave unpredictably. Shot one at a time, they create an interference pattern on the detector screen, as if each particle passes through both slits simultaneously, interfering with itself like a wave. But here's the twist. The moment scientists place a measuring device to observe which slit the particle actually goes through, the interference vanishes. The particles stop acting like waves and behave like discrete, localized objects. It's as if reality changes based on whether we're watching. Biocentrism takes this a step further. What if it's not just particles responding to measurement, but the universe itself molding around conscious observation? Imagine a tree falling in an empty forest. Common sense says it makes sound waves, but biocentrism asks, without an ear to translate those vibrations into sound, does the phenomenon truly exist as sound at all? This isn't just semantics, it challenges the very nature of existence. If reality is a tapestry woven by perception, then every observation, every measurement becomes a stitch binding the cosmos together. Critics argue this veers into solipsism, the idea that only one's mind is sure to exist. But biocentrism doesn't claim reality is imaginary. It proposes that consciousness is a fundamental force, like gravity, inseparable from the universe's structure. Think of it like a cosmic version of the observer effect on steroids. Just as a thermostat doesn't create temperature but regulates it, consciousness might not invent reality but participate in its manifestation. The implications ripple outward. If consciousness shapes reality, then entanglements, spooky connections, fractal patterns across scales, even the holographic principle, all might be facets of a deeper, observer-dependent unity. A bird's flight, a supernova's burst, the spin of an electron. In this view, they're not isolated events but notes in a symphony where consciousness is both composer and audience. So where does that leave us? If biocentrism holds, you're not just a bystander in the universe, you're a co-creator, your observations subtly shaping the quantum fabric of existence. It's a humbling, electrifying thought. The night sky isn't just something you see. In a very real sense, it's something you help create just by looking. Time might feel like an unstoppable river carrying us from one moment to the next, but what if that's just an illusion? Imagine the entire history of the universe laid out like a vast, unchanging sculpture where the Big Bang, the rise of civilizations, and every future event exist simultaneously, frozen in an intricate four-dimensional structure. This isn't science fiction, it's the block universe theory, a radical perspective where past, present, and future are equally real, permanently stitched into the fabric of spacetime like frames in a cosmic film reel. Einstein's theory of relativity hinted at this decades ago. Time, he showed, isn't absolute, it bends and stretches depending on gravity and motion. Two observers moving at different speeds or sitting near a black hole will experience time passing at wildly different rates. But relativity goes even further. It treats time as just another dimension, no different from length, width, or height. In this view, your life isn't a series of fleeting moments. It's more like a long, winding road, with every step you've taken and every step you'll ever take already etched into existence. The now you're experiencing is just your consciousness moving along that path, like a spotlight gliding across a darkened stage. Think of it like a book. From the outside, all its pages beginning, middle, and end exist at once. But when you read it, your focus moves chapter by chapter, creating the illusion of a story unfolding. The block universe suggests reality works the same way. Your birth, your first heartbreak, the last sunset you'll ever see, they're all fixed in place, part of an eternal now. Even events we consider future, like the death of distant stars or humanity's colonization of other planets, are already out there, waiting in the structure of space-time like unread pages. This raises a haunting question. If the future is already written, do we truly have free will? Some philosophers argue yes, our choices still matter because they're woven into the block's fabric. Every decision you make is like a turn in that unchanging road, part of what makes the universe's grand structure complete. Others see it as proof that free will is an illusion, that we're just passengers riding a predestined track through space-time. But here's where it gets even stranger. Quantum mechanics might offer a loophole. At the smallest scales, particles exist in probabilities until observed, suggesting the block universe could be more like a branching tapestry, with countless potential futures all equally real until one path is chosen. What does this mean for hidden connections? If time is a landscape rather than a line, then every event is eternally linked. A supernova exploding 1 billion years ago isn't just a distant memory. It's as present as the device in your hands right now, just at a different coordinate in space-time. The hands of a clock you wore as a child still tick in the past, forever part of the block. Even your future self, decades from now, is already out there in the cosmic weave, connected to you across time like points on a vast, unchanging map. So the next time you feel the weight of a past regret or the anxiety of an uncertain future, remember, in the block universe, they're not gone or unformed, they're just as real as this moment. You're not racing against time, you're exploring it one frame at a time in a masterpiece where every second is eternal. Rupert Sheldrake's theory of morphic resonance proposes something extraordinary, that nature has a memory, a kind of invisible blueprint that shapes everything from snowflakes to human behavior. Unlike traditional explanations that rely solely on genetics or physical laws, Sheldrake suggests that patterns become easier to repeat the more they occur, as if the universe itself is learning. Imagine a musician practicing a difficult piece. At first, the notes feel awkward and disjointed, but with repetition, they flow effortlessly. Now apply that same principle to reality itself. When a molecule forms a crystal for the first time, the theory claims it's breaking new ground. But once that structure exists somewhere in the universe, it becomes easier for other molecules to follow suit, as if the pattern leaves an imprint in a hidden field of information, Sheldrake's so-called morphic field. This isn't just about crystals. Take animal behavior, like the famous case of birds learning to open milk bottles. In the early 20th century, blue tits in England figured out how to peck through foil caps to steal cream. Shortly after, the behavior spread rapidly across the country, far faster than genetic mutation or direct observation could explain. Sheldrake argues this wasn't just imitation, it was morphic resonance at work. Once the pattern was established, it somehow became easier for other birds to replicate, almost as if the knowledge was telepathically shared. Skeptics dismiss this as coincidence, but similar examples abound. Lab rats in different parts of the world suddenly solving mazes faster than before, even when isolated from one another. Flowers adopting new pollination tricks that spread inexplicably across continents. If morphic resonance is real, it implies a universe where habits, not just laws, govern how things unfold. The implications ripple into human experience too. Have you ever felt a sudden, unexplainable surge of collective emotion, like a stadium of strangers cheering in perfect unison? Or noticed how certain inventions or discoveries seem to emerge simultaneously in different parts of the world, as if the idea was ripe for the taking? Sheldrake would argue these aren't just quirks of culture, they're evidence of morphic fields harmonizing human thought. Even language evolution could fit this mold. Words and grammatical structures might propagate not just through teaching, but through an invisible resonance that makes some patterns stick while others fade. Critics, of course, call this pseudoscience. They point out that morphic fields haven't been detected by instruments, and that simpler explanations, like selective attention or environmental cues, often account for the phenomena Sheldrake describes. Yet others counter that dark matter and quantum entanglement were once dismissed as fantasy too. The heart of the debate isn't just about evidence, but about the nature of causality itself. Is the universe a cold machine governed by fixed laws, or a living, learning system where habits accumulate like grooves in a record, guiding the needle of reality toward familiar rhythms? If morphic resonance holds even a grain of truth, it redefines connection in the cosmos. A butterfly's wing flap might not just cause a hurricane, it could subtly reinforce the very idea of flight across time and space, making future butterflies better at flying. Your morning coffee ritual might resonate with millions of others, strengthening the pattern of that first fragrant sip. It's a universe where repetition isn't just practice, it's participation in shaping reality itself. Whether true or not, the theory dares us to ask, what if the universe isn't just governed by physics but by memory? At the quantum level, empty space isn't empty at all. It's a seething, bubbling ocean of energy vibrating with infinite potential. This is the zero-point field, the lowest possible energy state of the universe, where particles flicker in and out of existence so fast they defy measurement. According to quantum mechanics, even in a perfect vacuum at absolute zero temperature, this frenetic activity never stops. It's as if the fabric of reality itself is alive with invisible motion, a cosmic hum underpinning everything we see. But what if this isn't just background noise? What if the zero-point field is the universe's hidden internet, a medium enabling instantaneous communication between every particle, every star, every conscious being? Take quantum entanglement, where particles mirror each other's states across vast distances. Conventional physics struggles to explain how this connection happens faster than light, but some theorists propose the zero-point field as the missing link. Imagine the field as a vast, invisible ocean, with every particle in the universe like a buoy bobbing on its surface. Tug one buoy and ripples spread instantly, not through the water but through the medium itself. In this view, entangled particles aren't sending signals, They're tuning into the same vibrations within the zero-point field, synchronized through its infinite energy. This idea stretches beyond the lab. If the zero-point field connects everything, it could explain phenomena like telepathy or intuition, not as supernatural, but as natural resonances within this quantum substrate. Studies have shown that human brainwaves exhibit patterns eerily similar to zero-point fluctuations, hinting that consciousness itself might tap into this field. Picture your thoughts as ripples in this cosmic pond, subtly influencing and being influenced by the wider universe. Even DNA has been theorized to interact with zero-point energy, with some experiments suggesting it absorbs and emits photons in ways that defy classical explanation. The implications are staggering. If information can traverse the zero-point field instantaneously, then the cosmos might be far more interconnected than we ever imagined. A supernova's explosion, a thought in your mind, the orbit of an electron, all could be nodes in a vast, invisible network humming with silent communication. Some researchers even speculate that dark energy, the mysterious force accelerating the universe's expansion, might arise from zero-point fluctuations, tying the fate of the cosmos to this quantum undercurrent. Skeptics argue that harnessing or detecting zero-point energy remains speculative, with no experimental proof of its role in information transfer. Yet the same was once said of gravitational waves, now a cornerstone of astrophysics. Whether the zero-point field is the glue binding reality or just another quantum curiosity, one thing is clear: the universe's empty space is anything but quiet. It's a symphony of hidden connections waiting to be heard, tearing through the fabric of space-time like invisible strands of cosmic spider silk. Cosmic strings are some of the most bizarre theoretical structures in the universe. These hypothetical one-dimensional flaws in reality, thinner than a proton yet denser than a neutron star, might be ancient relics from the universe's violent birth, frozen fractures in the cosmic ice left over from the Big Bang's explosive expansion. Picture the early universe cooling from an unimaginably hot, unified state, like molten metal solidifying. As it transitioned, cracks might have formed in the very structure of spacetime itself, not made of matter but pure energy, warping gravity around them with such intensity that a single inch of cosmic string could outweigh Mount Everest. What makes these filaments so extraordinary is their potential to stitch the cosmos together. Stretching across billions of light years, these strings could form a hidden lattice, a gravitational superhighway connecting distant galaxies in ways we're only beginning to theorize. If they exist, a cosmic string passing through our solar system would bend light around it, creating double images of stars or distorting the cosmic microwave background like a funhouse mirror. Some models even suggest that when strings intersect or vibrate, they might emit bursts of gravitational waves, ripples in spacetime detectable with today's observatories. The implications are staggering. These strings could be the universe's original wiring, threading through everything from galaxy clusters to quantum foam. Imagine two galaxies separated by vast distances, seemingly unconnected yet linked by a cosmic string vibrating beneath the surface of reality, transmitting energy or information instantaneously. It's like discovering the hidden scaffolding behind a painting, revealing that what we thought was chaos is actually held together by an intricate, invisible framework. Cosmic strings might also solve one of cosmology's biggest puzzles: why the universe is so uniform. The Big Bang's afterglow, the cosmic microwave background, shows eerie consistency in temperature across regions too distant to have ever been in contact. How strings could provide an answer. Like seams in a quilt, they might have forged connections between these regions during inflation, equalizing conditions before light could even traverse the gaps. But here's the wildest possibility: cosmic strings could be time machines. Their immense gravitational fields might twist spacetime into closed loops, creating pathways where time folds back on itself. A spaceship traveling alongside a string could, in theory, circle back to its own past, not by breaking the laws of physics, but by riding the contours of a space-time defect forged at the dawn of time. While no direct evidence of cosmic strings exists yet, astronomers hunt for their fingerprints in the warped light of distant quasars and the subtle patterns of the cosmic microwave background. Whether these phantom threads are real or not, their theoretical existence reminds us that the universe might be far more intricately woven than we ever dreamed, a tapestry where even the flaws tell a story. What if everything you've ever known, the stars, the air in your lungs, even the warmth of sunlight on your skin, is nothing but an elaborate digital illusion? The simulation hypothesis isn't just a plot twist from a sci-fi movie. It's a serious argument gaining traction among philosophers, physicists, and tech billionaires alike. The core idea is startlingly simple. Our universe might be an artificial construct, an ultra-advanced simulation running on some unfathomable computer, with every quark, every supernova, and every conscious thought just lines of code in a cosmic program. Philosopher Nick Bostrom framed this possibility as a trilemma, three stark options, one of which must be true. Either civilizations like ours almost always go extinct before developing simulation technology, or advanced societies lose interest in creating ancestor simulations, or we're almost certainly living in one right now. There's no fourth option. Bostrom's logic is cold and mathematical. If future civilizations could run countless simulations of their ancestors, the number of simulated minds would dwarf biological ones, making it statistically probable we're among the simulated. But this isn't just philosophical sleight of hand. Quantum physics might hold eerie clues. Take the observer effect, where particles behave differently when measured, as if the universe is optimizing processing power by only rendering reality when observed. Or entanglement, where particles sync instantaneously across light years, defying locality, just like data packets in a networked simulation skipping normal delays. Even the pixelated nature of reality fits. Planck length, the smallest possible unit of space, could be the universe's resolution limit, its pixel size. Then there's the Fermi paradox. If the universe is teeming with life, why is it so silent? One unsettling answer: the simulation hasn't rendered other civilizations yet, or they're intentionally quarantined to keep us from discovering the truth. Glitches in the code might explain déjà vu, UFO sightings, or even Mandela effects, collective false memories that could be patches or updates rolled out imperfectly. Critics argue this is unfalsifiable, a modern-day solipsism dressed in tech jargon, but proponents counter that we might find evidence. If the universe is a simulation, it would have computational limits. Physicists have hunted for anomalies in cosmic ray energies that might reveal a frame rate or grid-like structure to spacetime. Others suggest that quantum randomness isn't random at all, but pseudo-random, like the predetermined random numbers in a video game. The simulation hypothesis forces us to confront profound questions. If we're just data in some higher reality, do our choices matter? Is the programmer a god, a teenager in a basement, or an AI recursively simulating itself? And if we one day create simulations indistinguishable from reality, how could we ever prove we're not already inside one? Whether true or not, this theory reshapes our cosmic perspective. Reality might not be the ultimate layer, just one nested in an infinite digital onion, where every universe is someone else's simulation, and every simulation holds universes of its own. If parallel universes exist, could they still be whispering to each other across the unfathomable gulf of reality? Quantum entanglement defies our classical intuition by linking particles instantaneously. But what if entire universes share this eerie connection? Some physicists speculate that in the infinite tapestry of the multiverse, neighboring realities might not be wholly separate. Instead, they could remain quantum entangled, their fates forever intertwined like cosmic twins sharing an invisible thread. Picture two soap bubbles floating side by side, their surfaces nearly touching. Though distinct, the slightest vibration on one affects the other through subtle, unseen forces. Now imagine those bubbles as entire universes, each with its own laws, stars, and civilizations. If entangled at their birth, perhaps during the inflationary period following the Big Bang, tiny quantum fluctuations in one universe might ripple into another, creating eerie synchronicities across realities. These universal interference patterns could explain phenomena that seem to break the rules of probability. Take déjà vu, for instance, that uncanny feeling you've lived a moment before. Mainstream science blames it on brain glitches, but could it be a fleeting resonance with a parallel version of yourself experiencing the same event in another timeline? Or consider the Mandela effect, where large groups misremember historical details identically. Skeptics call it collective false memory, but what if it's a faint overlap between universes with subtly diverging histories? The math behind this idea isn't pure fantasy. In certain interpretations of quantum mechanics, like the many worlds theory, every quantum decision spawns branching universes. But crucially, these branches don't sever completely. They remain part of a single, ever-expanding quantum wave function. Some theorists propose that under rare conditions, these branches might interfere with one another, like overlapping ripples in a pond. Evidence could even be hiding in plain sight. Unexplained statistical anomalies like particles behaving slightly off in repeated experiments might be signatures of interference from other universes nudging our own. Think of it like tuning a radio. Most of the time you hear one clear station, your home universe, but static crackles in the background could be signals bleeding through from adjacent frequencies, other realities brushing against yours. If true, then every choice you make might resonate across the multiverse, echoing in versions of you living different lives. The implications are dizzying. A breakthrough in one universe could subtly influence another's scientific progress. A tragedy avoided here might still haunt you, or a version of you somewhere else. Critics argue this stretches quantum theory beyond recognition, that entanglement can't scale to entire universes without violating energy conservation or causality. Yet others counter that our grasp of physics is still in its infancy. After all, black holes and dark energy once seemed impossible too. Whether real or not, multiverse entanglement forces us to confront a humbling idea. Reality might be far more fluid, far more connected than we ever dared believe. Your life, your world, might not be an isolated story, but one thread in an infinite tapestry, vibrating in harmony with countless others you'll never see. Deep within the mystical traditions of ancient India lies a concept so profound it bridges spirituality and cutting-edge physics, the Akashic Records. Described as an ethereal library woven into the fabric of existence, this cosmic archive is said to hold every thought, action, and event that ever was or will be. Imagine the universe as a vast, timeless hard drive where the birth of stars, the fall of civilizations, and even your most fleeting childhood memory are eternally inscribed in an immaterial medium called Akasha, a Sanskrit word meaning sky or ether. While this idea might sound like fantasy, modern physics is stumbling upon eerily similar notions, suggesting that reality itself might function as a grand recording device. The holographic principle offers a striking parallel. Just as the Akashic Records propose that information is preserved in a non-physical realm, physicists like Leonard Susskind argue that all three-dimensional reality could be projected from a two-dimensional surface at the universe's edge, a cosmic hard drive where data is stored with perfect fidelity. Black holes amplify this connection. When matter vanishes beyond an event horizon, its information isn't destroyed. It's imprinted onto the horizon's surface, much like an entry in the Akashic ledger. The universe, it seems, has a way of keeping receipts. Quantum memory adds another layer. Experiments show that particles can retain memory of their past interactions, influencing future behavior in ways that defy classical physics. This phenomenon, called quantum Darwinism, suggests that information about a system spreads into its environment, creating a kind of natural archive accessible to observers. It's as if the universe is constantly broadcasting its history into the quantum foam, allowing fragments of the past to persist like whispers in space-time. The Akashic Records, then, might not be a mystical abstraction but a poetic foreshadowing of physics' deepest truths. The real intrigue lies in the overlap between ancient intuition and modern discovery. Seers and mystics access the Akashic Records through meditation or altered states, describing it as a luminous web of interconnected knowledge. Today, scientists probing quantum entanglement or the holographic universe echo this imagery, with entangled particles acting like nodes in a cosmic network, instantly sharing information across vast distances. Both perspectives, one spiritual, one scientific, converge on a startling idea. Nothing is ever truly lost. Every laugh, every supernova, every act of love or violence might ripple through this hidden substrate, leaving traces that endure long after the moment passes. Skeptics dismiss the Akashic Records as pseudoscience, and rightly so. There's no empirical proof of an etheric library. Yet the mere fact that physics keeps bumping into versions of this concept should give us pause. Whether through the holographic universe, quantum memory, or the zero-point field, science is grappling with the same profound question posed by the ancients. Is reality fundamentally a tapestry of information? If so, then the line between mysticism and physics blurs, inviting us to consider that the universe might not just contain knowledge, it might be knowledge written in a code we're only beginning to decipher. So the next time you gaze at the stars, ponder this. Your life, your dreams, even your regrets might already be etched into the cosmos, not as fading echoes, but as permanent lines in the universe's grand story. Whether you call it Akashic or quantum, the message is the same. Nothing is ever truly forgotten. What if the universe itself is alive, not in the poetic sense, but as a vast, self-regulating organism where galaxies act like cells and cosmic filaments pulse with a kind of gravitational metabolism? This is the audacious leap of the Gaia hypothesis extended to cosmic scales. James Lovelock's original idea painted Earth as a single, self-balancing entity, where oceans, atmosphere, and life collaborate to maintain conditions for survival. But stretch this vision across light years and something breathtaking emerges, a universe that might not just contain life but behave like it. Take galaxy clusters, those sprawling metropolises of stars bound by gravity. Observations reveal they don't just drift aimlessly, they evolve in cycles, recycling gas and energy in ways eerily reminiscent of biological systems. Stars explode as supernova, seeding space with heavy elements that birth new stars, much like fallen leaves nourish soil for future growth. Black holes at galactic centers act as regulatory hearts, their jets pumping energy into surrounding space, preventing runaway star formation. Even dark matter, that enigmatic scaffold, could function like a cosmic nervous system, its invisible threads transmitting gravitational signals that shape large-scale structure. Some theorists go further, suggesting the universe exhibits homeostasis, a self-correcting balance akin to a body regulating temperature. The cosmological constant, the force driving the universe's acceleration, might not be a fixed number but a dynamic response to cosmic conditions. Imagine a feedback loop where expansion triggers subtle adjustments in dark energy's strength, maintaining equilibrium across epochs. It's as if the universe knows how fast to grow, fine-tuning its own expansion to avoid collapse or dissipation into nothingness. Even more provocative is the idea of cosmic reproduction. Could universes spawn new universes through black holes or quantum fluctuations, passing down genetic traits like fundamental constants? Lee Smolin's theory of cosmological natural selection posits exactly this, that universes favoring black hole production survive by creating offspring with similar physics. In this view, our universe's fine-tuned laws perfect for stars, planets, and life aren't luck. They're the result of a Darwinian dance playing out across multiversal generations. Critics argue this anthropomorphizes nature, projecting biology onto inert physics. Yet the parallels are hard to ignore. Slime molds solve mazes without brains. Ant colonies exhibit collective intelligence. If simplicity can mimic life's rhythms, why not complexity on a galactic scale? The Milky Way's spiral arms, for instance, aren't static, they ripple with density waves, a dynamic pattern resembling the pulsing veins of a leaf. The implications are profound. If the universe self-regulates, then intelligence might not be an accident, it could be part of the system's immune response, a way for the cosmos to understand and sustain itself. Your curiosity about the stars, the equations scribbled by a physicist, even this video might all be threads in a universal tapestry far more interconnected than we ever dreamed. The night sky isn't just something we observe. In this vision, it's something we're part of, a living whole whispering its secrets to those willing to listen. Imagine the universe crackling with invisible rivers of electricity, weaving together stars and galaxies in a cosmic circuit billions of light years wide. This isn't the plot of a futuristic saga, it's the core idea behind the electromagnetic universe theory, a radical alternative to mainstream cosmology that puts magnetism and plasma, not just gravity, at the heart of cosmic architecture. While Einstein's relativity paints the cosmos as a gravitational ballet, this framework suggests something far more dynamic, a universe alive with electric currents, where filaments of ionized gas sculpt galaxies and power quasars like wires in a celestial switchboard. At the center of this vision lies plasma, often called the fourth state of matter, a seething sea of charged particles that makes up over 99% of the visible universe. Unlike neutral gas, plasma conducts electricity and responds to magnetic fields, allowing it to form structures that defy gravity's slow pull. In labs, when physicists run high-voltage currents through plasma, they produce intricate webs of filaments that twist and braid, eerily mimicking the vast tendrils of galaxies observed in deep space surveys. These aren't just rough resemblances. The similarities are so precise that some researchers argue gravity alone can't explain them. Enter Birkeland currents, named after Norwegian scientist Christian Birkeland, who first proposed in the early 20th century that Earth's auroras were powered by streams of charged particles from the sun. Today, astronomers see these currents everywhere, in the twisting arms of spiral galaxies, the jets erupting from black holes, even the gargantuan structures connecting galaxy clusters across the void. Picture these currents as cosmic power lines, channeling electricity across interstellar space, lighting up stars like bulbs on a string. When two currents intertwine, they can pinch plasma into dense knots, possibly birthing stars without the need for collapsing gas clouds. The implications rewrite cosmic history. Take galactic formation. Mainstream models rely on dark matter's gravitational tug to gather gas into galaxies over eons. But plasma cosmology suggests electromagnetic forces could assemble galaxies much faster, with currents sculpting spiral arms and fueling quasars in bursts of energetic feedback. Even black holes might owe their voracious appetites to these currents, funneling plasma into their maws like water down a drain, and when galaxies collide. Instead of a slow gravitational dance, imagine a catastrophic short circuit, unleashing particle tsunamis that glow in X-rays, exactly what telescopes detect in merging clusters like the famous bullet cluster. Critics dismiss this as fringe science, pointing out that while lab plasmas behave similarly at small scales, extrapolating to galactic proportions remains controversial. Yet the theory scores surprising wins. NASA IBEX mission mapped the Sun's magnetic field interacting with interstellar plasma, revealing a filamentary structure resembling scaled-down galactic filaments. Meanwhile, radio telescopes keep finding synchrotron radiation, a telltale signature of high-speed electrons spiraling in magnetic fields woven through galaxy clusters, hinting at unseen currents. Whether the electromagnetic universe theory ultimately holds up or not, it forces us to confront a humbling truth. We've barely begun to map the universe's hidden wiring. The same forces that light up neon signs on Earth might also be shaping the grandest structures in existence, humming with a power we're only starting to measure. So the next time you see a thunderstorm flicker with lightning, remember, you're glimpsing a tiny spark of the same force that could be knitting the cosmos together. Staring at a slice of brain tissue under a microscope, you'd see a dizzying web of neurons branching, interconnecting, pulsing with electrical signals. Now zoom out to a telescope's view of the cosmos, and something uncanny emerges. Galaxy clusters strung along vast filaments, threading through the darkness in patterns that mirror the brain's neural highways. This isn't just a poetic coincidence, it's a mathematical reality. Studies comparing cosmic surveys to neural imaging reveal nearly identical structures, with galaxies clustering like neurons around synapses and cosmic voids echoing the empty spaces between brain cells. The similarity is so striking that physicists and neuroscientists have begun collaborating, asking a mind-bending question: could the universe itself be thinking? The numbers are hard to ignore. In 2020, a team of astrophysicists and computational biologists published a groundbreaking analysis comparing the cosmic web to neural networks in the human cerebellum. Using algorithms designed to map brain connectivity, they found both systems share startling statistical traits: the same clustering behavior, similar numbers of connections per node, even matching patterns of long-range filaments bridging dense hubs. The cosmic web and the brain aren't just vaguely alike. They appear to follow identical mathematical blueprints for organizing complexity. But how? One compelling explanation lies in the physics of network formation. Both neurons and galaxies evolve under tension between two forces, attraction and resistance. In the brain, neurons grow toward chemical signals while competing for space and resources. In the universe, gravity pulls matter into dense knots while dark energy drives space itself apart. The result, in both cases, is a fractal-like web where efficiency reigns. Information or matter must flow quickly between nodes without overloading any single pathway. Nature, it seems, has a universal playbook for building interconnected systems, whether inside a skull or across a billion light-years. Some theorists take this even further. If the universe's structure resembles a neural network, could it also function like one? The brain's power comes from its ability to process and transmit information. So what if the cosmos does the same? Dark matter filaments might not just passively guide galaxies. They could act as conductive pathways for some unknown form of cosmic communication. Stars could be nodes processing energy like neurons firing, while black holes serve as hubs integrating and redistributing information. Even the universe's expansion might mirror the brain's plasticity, constantly rewiring itself in response to internal feedback. Skeptics argue this is anthropomorphism run wild, seeing faces in clouds. Yet the math persists. When researchers simulate cosmic evolution using neural network models, the results align eerily with observed galaxy distributions. Meanwhile, studies of brain activity find it follows the same power law distributions as galaxy clustering, a hallmark of scale-free systems where patterns repeat at every level. Whether by shared physics or sheer cosmic irony, the parallels refuse to fade. Here's the profound takeaway. If the universe and the brain are built alike, then consciousness might not be an accident. It could be an inevitable expression of how information organizes itself at scale. Your thoughts, your memories, even your sense of self might not be separate from the cosmos. They could be part of its rhythm, a local echo of a pattern written into the fabric of reality itself. The night sky in this light isn't just something you observe, it's something you're woven into, a neural thread in a thinking universe. Gravity, the most familiar force in our daily lives keeping us grounded, shaping the orbits of planets, is also the most mysterious when we zoom into the quantum realm. While electromagnetism and the nuclear forces have been tamed by quantum theory, gravity stubbornly resists, its cosmic dominance collapsing into incoherence at subatomic scales. Enter loop quantum gravity, a radical framework that doesn't just reconcile gravity with quantum mechanics. It suggests space-time itself is stitched together from a shimmering web of interconnected threads, a fabric so fine it rewrites our understanding of reality's deepest layer. Picture space-time not as a smooth continuum, but as a tapestry of microscopic loops, each a billion trillion times smaller than an atom. These loops aren't floating in space, they are space, woven together into dynamic networks that vibrate and evolve. Think of a chainmail glove, rigid up close but flexible when viewed from a distance, mimicking the smooth curves of Einstein's relativity. Now imagine that glove spanning the universe, with every loop carrying a quantum of area or volume, a pixel of space-time itself. This is the essence of loop quantum gravity. A universe where geometry is granular, where the endless void is actually a kaleidoscope of finite, humming connections. At the heart of this theory lie spin networks, intricate graphs that map how these quantum loops intertwine. Each node represents a tiny chunk of space, while the links between them encode how these chunks relate, like a cosmic subway map where stations are volumes of reality and tracks are the quantum threads binding them. The spin in spin networks isn't just metaphor, it comes from angular momentum, a fundamental property borrowed from particle physics. When these networks evolve, they don't move through time, they generate time, their shifting configurations creating the illusion of a flowing present. A black hole singularity, in this view, isn't a point of infinite density but a place where the network's weave tightens to its smallest possible stitch. What makes this vision so transformative is how it handles entanglement. In standard quantum mechanics, entangled particles share a spooky connection across space. But in loop quantum gravity, their link might be literal, their properties woven into the same spin network, like two beads strung on a single thread. This could explain entanglement's instantaneity without breaking relativity. The particles aren't signaling across space, they're tapping into a deeper, geometric bond encoded in spacetime's very fabric. The implications ripple outward. Cosmic inflation, the universe's explosive early growth, might have been a phase transition in the spin network, a sudden unraveling and reweaving of quantum threads. Dark energy could arise from tension in the network's weave, like a stretched spring pushing space apart. Even the Big Bang might not have been a singularity, but a rebound from a prior universe's collapse, its spin networks unraveling only to knit themselves anew. Critics argue the theory remains untested, lacking the clear predictions that would make it mainstream. Yet its mathematical elegance is undeniable, and recent simulations show spin networks can spontaneously generate four-dimensional spacetime, hinting at a universe where dimensionality itself emerges from quantum connections. Whether loop quantum gravity ultimately holds or not, it dares us to imagine reality not as a stage where particles dance, but as the dance itself, a fluid, dynamic weave where every thread is a bond, and every bond tells a story older than time. Time crystals sound like something ripped from a science fiction novel, structures that pulsate with perpetual motion, not in space but in time itself. Nobel laureate Frank Wilczek first proposed this bizarre form of matter in 2012, envisioning a system that doesn't just exist in equilibrium but breaks time symmetry, oscillating endlessly without energy input. Think of a clock that ticks forever without winding, or a diamond where atoms don't just sit in a lattice but dance in an eternal rhythm. Now stretch that idea to cosmic proportions. What if the universe itself is a time crystal, its very fabric humming with synchronized oscillations that span from quantum particles to galactic superclusters. Wilczek's hypothesis starts with a simple but profound observation. Ordinary crystals like snowflakes or salt break spatial symmetry, repeating their atomic patterns in space but remaining static in time. Time crystals flip this script, repeating their patterns in time while appearing motionless in space. In a lab, physicists have created tiny versions of these using chains of ions or defects in diamonds, where quantum effects lock particles into rhythmic cycles. But the universe, with its mind-bending scale, might be the ultimate time crystal, its fundamental fields and forces pulsing in a grand, coordinated beat. Imagine the cosmic microwave background, the afterglow of the Big Bang, as more than a static snapshot. What if its subtle temperature fluctuations aren't just frozen relics, but the imprint of a universe-wide oscillation, a rhythm set in motion at creation and still resonating today? Dark energy, the mysterious force accelerating cosmic expansion, could play a role here, its constant pressure acting like a metronome, driving the universe's expansion and contraction at scales we can't yet measure. Even black holes might participate, their event horizons vibrating in sync with these hidden temporal waves, threading the cosmos together like drumheads tuned to the same frequency. The implications are staggering. If the universe is a time crystal, then its apparent uniformity, the way distant galaxies move in similar ways despite never having interacted, might not be coincidence but orchestration. Just as synchronized pendulums eventually match their swings through subtle energy transfer, galaxies separated by billions of light years could be locked in a cosmic dance, their motions harmonized by underlying temporal patterns. This could explain oddities like galaxy rotation curves, where stars orbit too fast for the visible matter present without invoking dark matter. Instead of invisible particles tugging on stars, their motions might be entrained by the universe's intrinsic oscillations. Critics argue that time crystals as we know them are too fragile to survive cosmic expansion, let alone dictate large-scale structure. Yet Wilczek counters that the universe's sheer size could stabilize these rhythms, with quantum effects at microscopic scales amplifying into macroscopic order, much like how trillions of tiny water molecules coalesce into a tsunami. The key lies in nonlinear dynamics, where small, localized vibrations cascade into system-wide coherence. Perhaps the most poetic possibility is that time itself emerges from these oscillations. Just as sound needs a medium to propagate, the flow of time might arise from the universe's crystalline vibrations, with every tick of your clock a shadow of the cosmic metronome. The next time you catch yourself humming a tune or tapping your foot to a rhythm, consider this. You might be echoing the pulse of reality itself, a fleeting participant in the universe's eternal dance. What if consciousness isn't something the universe produces like steam rising from a kettle, but something it's fundamentally made of? This is the bold claim of panpsychism, a theory that turns our understanding of reality inside out. Instead of assuming consciousness emerges from complex systems like brains, panpsychism suggests it's woven into the fabric of existence itself, present even in the tiniest particles. Think of it like this: just as mass and charge are intrinsic properties of matter, so too might be a rudimentary form of awareness. A photon flying through space or an electron orbiting an atom wouldn't just be a mindless object, it might possess a faint glimmer of subjective experience, a whisper of what it's like to be that particle. This idea isn't as far-fetched as it sounds. Consider the hard problem of consciousness posed by philosopher David Chalmers. Neuroscience can map brain activity to thoughts and feelings, but it can't explain why those electrical signals feel like anything at all. Why isn't the brain just a silent, self-operating machine? Panpsychism offers an elegant solution, because feeling isn't something the brain manufactures, it's something the universe has always had. When particles organize into complex structures like brains, These micro-experiences combine, amplifying into the rich inner lives we recognize as human consciousness. It's like pixels forming an image. Individually, they're just dots of color. Together, they create a picture. Quantum mechanics adds tantalizing weight to this view. At the subatomic level, particles behave differently when observed, as if aware of being measured. A phenomenon even Nobel laureate Eugene Wigner speculated might hint at consciousness playing a role in reality's structure. Entanglement, where particles remain mysteriously linked across space, could reflect a deeper layer of shared experience. If panpsychism holds, then every interaction in the universe, from atoms bonding to galaxies colliding, might carry a subtle thread of connection, an exchange not just of energy but of experience. Critics argue this is anthropomorphism gone wild, projecting human qualities onto mindless matter. Yet panpsychism avoids the pitfalls of both materialism and dualism. Unlike materialism, it doesn't struggle to explain how consciousness magically appears from non-conscious parts. Unlike dualism, it doesn't require a mystical soul separate from physics. Instead, it proposes a seamless spectrum, from the faintest flicker of awareness in a quark to the symphony of self-reflection in a human mind. The implications are cosmic. If consciousness is universal, then the universe isn't just alive, it's awake, a vast network of sentient nodes communicating through quantum whispers. Your thoughts might resonate with the atoms in a distant star, not through magic, but through the shared fabric of experience. The night sky wouldn't just be a scattering of lights, it would be a collective dream, a tapestry of infinite perspectives woven into a single, shimmering whole. Whether true or not, panpsychism dares us to reconsider our place in the cosmos, not as observers standing apart, but as participants in a universe that feels, knows, and connects in ways we're only beginning to imagine. Mathematics isn't just a tool we use to describe the universe, it might be the universe. That's the radical proposition of physicist Max Tegmark's mathematical universe hypothesis, which suggests that reality isn't merely modeled by math but is fundamentally made of it. In this view, the cosmos isn't a physical structure running on mathematical rules. It is a mathematical structure, an abstract equation that has somehow become self-aware. Imagine a cosmic spreadsheet where every galaxy, every atom, even your thoughts, are just cells in an infinite calculation unfolding across dimensions. Tegmark's argument hinges on a startling observation. The more precisely we probe nature, the more it seems to dissolve into pure math. Particles aren't tiny marbles, they're probability waves described by Schrödinger's equation. Space-time isn't a static stage, it's a dynamic fabric bending under Riemannian geometry. Even the constants governing reality, like the speed of light or the charge of an electron, appear fine-tuned to mathematical elegance. This isn't just convenient modeling, it's as if we're hacking into the universe's source code and finding nothing but numbers and symbols. The implications unravel like a fractal. If reality is mathematical, then every possible mathematical structure, from the simplest equation to hyper-dimensional algebras, must exist somewhere in the multiverse. Our universe, with its 3 spatial dimensions and 4 fundamental forces, is just one page in an infinite textbook of mathematical possibilities. In another chapter, a universe governed by hyperbolic geometry might host living crystals that think in calculus. Elsewhere, a cosmos built on knot theory could birth civilizations that perceive time as a Möbius strip. This isn't just speculative philosophy. Tegmark points to quantum superposition as evidence. When a particle exists in multiple states until measured, it's not switching between physical configurations, it's oscillating between mathematical solutions. The act of observation doesn't collapse a wave function into reality. It selects one branch of a pre-existing equation. Even entanglement's spooky connections make eerie sense. 2 particles aren't communicating faster than light. They're manifestations of a single, indivisible mathematical object. Critics argue this reduces existence to a sterile abstraction, stripping away the richness of subjective experience. Yet Tegmark counters that consciousness itself could be a mathematical pattern, a specific type of information processing that emerges when equations reach sufficient complexity. Your joy, your memories, even the scent of rain might just be intricate algorithms running on the hardware of space-time. The most profound consequence is connection. If all mathematical structures exist, then every theorem, every proof, every elegant formula is a gateway to an actual universe. The Pythagorean theorem isn't just a classroom exercise, it's a skeletal blueprint for a possible reality. When mathematicians explore imaginary numbers or non-Euclidean geometries, they might unknowingly be mapping alien cosmoses. Even a child doodling shapes could be sketching the faint outline of a world. This transforms how we see knowledge. Discovering laws of physics isn't uncovering nature's secrets, it's remembering fragments of a grander equation we're embedded within. The night sky isn't a random scattering of stars, it's a shimmering page of a cosmic textbook, inviting us to read deeper. Whether Tegmark's hypothesis holds or not, it dares us to consider that the universe isn't just written in the language of mathematics. It is the language, and we're the syllables it's learning to pronounce. What if our entire universe, every galaxy, every star, every living creature, exists inside a black hole from another, grander cosmos? This isn't just a wild thought experiment, it's a serious hypothesis gaining traction among physicists. The idea hinges on a strange symmetry between how black holes behave and how our universe began. When matter collapses into a black hole, it doesn't just vanish. According to the holographic principle, all the information about what falls in gets encoded onto the black hole's event horizon, the point of no return. Now flip that around. If our universe emerged from a singularity in a parent universe's black hole, the holographic principle suggests that everything we see might just be a projection from a two-dimensional boundary far beyond our cosmic horizon. Think of it like a Russian nesting doll of realities. In the parent universe, a massive star collapses, forming a black hole. Inside that black hole, the crushing gravity doesn't just create a dead end, it sparks a new expansion, a big bang birthing a universe of its own. This isn't pure fantasy. The equations describing black hole singularities and the Big Bang's initial conditions look eerily similar, almost as if they're two sides of the same cosmic coin. If true, then the black holes in our universe could themselves contain entire worlds, branching endlessly like a fractal tree of existence. The holographic principle adds another layer. Just as a black hole's interior is encoded on its surface, our universe's three-dimensional reality might be a hologram projected from data stored on a distant two-dimensional boundary. That boundary could be the event horizon of the parent black hole, meaning all the information about our cosmos, every particle, every law of physics, is written on a surface we'll never see. This creates a mind-bending kind of hidden connection. Events in our universe, from supernova to human thoughts, might be echoes of information processing happening on that primordial horizon. Here's where it gets even stranger. If our universe is inside a black hole, then the parent cosmos's laws might imprint onto ours like a cosmic DNA. The speed of light, the strength of gravity, even the number of dimensions we experience could be inherited from the physics of the outer universe. This could explain why our universe seems so finely tuned for life, because it's not random. It's a carefully structured offspring of a higher reality. Critics argue there's no way to test this idea, no signal or observation that could confirm we're living in a black hole. Yet clues might be hiding in the cosmic microwave background, the afterglow of the Big Bang. Certain anomalies in its temperature patterns, like circular bruises in the radiation, could theoretically be imprints from our parent universe's gravitational waves, ripples left from the black hole's violent birth. Others look for signs in how black holes in our cosmos behave, searching for hints that they too might contain universes Whether true or not, this theory reshapes our place in the cosmos. If we're inside a black hole, then every star in the night sky isn't just a distant sun. It's part of a grand, nested chain of realities reaching upward and downward forever. The universe isn't merely vast, it's layered, a hall of mirrors where every shadow contains a world. And if black holes are cosmic wombs, then even in the darkest corners of space, new beginnings might always be stirring. Lightning crackles across the sky, a fleeting glimpse of the invisible electric forces that might shape the cosmos itself. The electric universe theory challenges mainstream astronomy's gravity-centric view with a radical alternative. Interstellar space isn't an empty void, but a seething ocean of plasma threaded with colossal currents that sculpt galaxies, ignite stars, and weave unseen connections across billions of light years. Imagine the universe not as a lonely expanse of isolated islands, but as a cosmic circuit board where filaments of ionized gas act like celestial wires humming with electromagnetic energy. At the heart of this idea lies plasma, the fourth state of matter, where atoms shed their electrons to form a conductive soup of charged particles. Plasma makes up over 99% of the visible universe, from the shimmering auroras around planets to the superheated jets erupting from black holes. In labs, when physicists subject plasma to high voltages, it self-organizes into twisting filaments and glowing double-layer structures eerily resembling the vast tendrils connecting galaxy clusters. The Milky Way's spiral arms, the looping prominences of the Sun, even the gargantuan radio lobes stretching from quasars, all could be manifestations of electromagnetic forces operating on scales we're only beginning to map. Take Birkeland currents, named after visionary physicist Christian Birkeland, who first proposed in the early 1900s that charged particles from the Sun powered Earth's auroras. Today, astronomers detect these currents everywhere, in the braided magnetic fields of galaxies, the corkscrew jets of young stars, even the enigmatic radio bridges linking colliding galaxy clusters. These aren't gentle flows, they're cosmic-scale lightning bolts, carrying enough energy to power star formation or rip molecular clouds apart. When two currents intersect, they can pinch plasma into dense knots, potentially igniting stars without relying on gravitational collapse. It's as if the universe runs on a hidden electrical grid, with galaxies as glowing nodes in a circuit we're just learning to trace. The implications rewrite cosmic history. Mainstream models attribute galaxy formation to dark matter's gravitational pull, a slow process taking billions of years. But plasma cosmology suggests electromagnetic forces could assemble galaxies far faster, with currents acting like cosmic conveyor belts, funneling matter into swirling disks. Even supermassive black holes might owe their existence to these currents, their voracious appetites fed by electromagnetic vortices spiraling matter inward at relativistic speeds. When galaxies collide, the result wouldn't just be a stately gravitational dance, but a violent short circuit, unleashing particle tsunamis detectable as X-ray bursts, exactly what telescopes observe in systems like the Taffy galaxies, where two galaxies appear welded together by luminous gas. Critics dismiss this as fringe science, pointing to gaps in quantitative predictions and the dominance of gravity at large scales, yet the theory scores uncanny hits. NASA IBEX mission mapped filamentary structures in the Sun's magnetic field interacting with interstellar plasma, structures scaled-down versions of galactic filaments. Meanwhile, astronomers keep finding synchrotron radiation, a telltale signature of electrons spiraling in magnetic fields permeating galaxy clusters, hinting at hidden currents. Perhaps most provocatively, the cosmic web's filamentary structure, long attributed to dark matter's gravitational scaffolding, could equally arise from plasma's self-organizing tendencies under electromagnetic forces. What if these currents don't just shape matter, but connect it? Plasma's conductivity means disturbances in one region could propagate almost instantaneously across vast distances, like a flicked switch illuminating a continent-spanning grid. A solar flare erupting in one star system might induce voltage surges in another light years away, synchronizing stellar activity without any observable signal. Ancient myths spoke of celestial harp strings vibrating between stars. The electric universe suggests they weren't entirely wrong. Whether this framework ultimately holds or not, it forces us to confront a humbling truth. We've barely begun to decipher the universe's hidden wiring. The same forces that power neon signs and lightning storms might also govern the birth of galaxies and the fate of stars. So the next time you see a thunderbolt split the sky, remember, you might be witnessing a microscopic spark of the same force that stitches the cosmos together. The universe hums with computation, not just metaphorically, but literally. According to physicist Seth Lloyd, reality might not merely resemble a computer. It could be an immense quantum processor where every particle, every photon, even the fabric of spacetime itself, is engaged in a ceaseless dance of information processing. This isn't science fiction, it's a rigorous theory suggesting that the cosmos operates by flipping quantum bits or qubits at the smallest scales, weaving the entire tapestry of existence through a grand, interconnected calculation. At the heart of this idea is quantum mechanics' most radical feature, superposition. Unlike classical bits that are either 0 or 1, qubits can exist in both states simultaneously, enabling parallel computations on a cosmic scale. Picture a star not just as a ball of plasma, but as a node in a sprawling quantum network, its photons carrying information as they radiate into space. Even the void between galaxies might crackle with computational activity as quantum fields fluctuate in a continuous exchange of data. In this view, the Big Bang wasn't just an explosion of matter. It was the universe booting up, initializing its first qubits in a fireball of potential. What makes Lloyd's hypothesis so compelling is how it bridges the abstract and the tangible. Take photosynthesis, where plants convert sunlight into energy with near-perfect efficiency. Experiments suggest this process might exploit quantum coherence, with photons testing multiple pathways at once, like a quantum computer optimizing a solution in real time. Scale this up, and you could imagine galaxies performing similar computations, their gravitational interactions processing information as they spin and collide. Even black holes, those infamous destroyers of information, might play a role as cosmic memory banks, encoding data on their event horizons before slowly radiating it back out as Hawking radiation. But the real revelation lies in connectivity. If the universe is a quantum computer, then entanglement, those spooky links between particles, isn't just a curiosity, it's the universe's wiring. Every entangled pair forms a qubit network, with changes in one instantly updating the state of another, no matter the distance. This could explain why reality appears so finely synchronized, from the uniformity of the cosmic microwave background to the delicate balance of physical constants. The universe isn't just governed by laws, it's executing them, computing its own evolution in a self-referential loop. Critics argue that calling the universe a computer is just poetic metaphor, that computation requires an external programmer which the cosmos lacks. Yet Lloyd counters that self-organization is computation's essence. A falling rock doesn't need instructions to calculate its trajectory. It simply follows physical laws, which are the computation. The universe, in this light, isn't running a program, it is the program. Its output, the very reality we experience. The implications are staggering. If the cosmos computes itself into existence, then consciousness might be a localized expression of that process, a subroutine in the universal code. Your thoughts, your perceptions, even your sense of self could be part of the universe's ongoing calculation, a fleeting pattern in the cosmic processor. This blurs the line between observer and participant, suggesting that by merely existing, we're not just reading the universe's output, we're helping write it. So the next time you feel the warmth of sunlight or gaze at the stars, consider this. You might be witnessing the universe thinking aloud, its infinite qubits shimmering with the answer to a question we're only beginning to ask. Imagine a universe where every star, every atom, every fleeting thought is just the visible ripple of something far deeper, an ocean of hidden connections folding and unfolding beneath the surface of reality. This is the essence of physicist David Bohm's revolutionary implicate order, a cosmic blueprint where separateness is an illusion and everything is intimately woven together in ways our senses can't perceive. At first glance, the world seems made of distinct objects, trees, planets, people, but Bohm argued this is merely the explicate order, the unfolded projection of a richer, more entangled dimension where boundaries dissolve. Think of it like watching a movie. The images on screen appear separate and sequential, but they're all encoded in the spinning reels hidden inside the projector. The universe, Bohm suggested, works the same way. Quantum mechanics offers startling clues to this hidden unity. Take non-locality, where entangled particles instantaneously mirror each other's states across vast distances. Einstein called it spooky action at a distance, but Bohm saw it as evidence of a deeper layer where all points are connected. In his model, particles aren't independent entities. They're dynamic expressions of a unified field, like whirlpools in a flowing river. The river's currents, the implicate order, give rise to the whirlpools, the explicate world, but the water itself is always continuous. This could explain why measuring one entangled particle affects its partner faster than light. At the implicate level, they were never truly apart to begin with. Bohm's vision finds eerie echoes in everyday experience. Consider a hologram, shatter it into pieces, and each fragment still contains the entire image, just at lower resolution. Similarly, in the implicate order, every part carries the whole. A single drop of seawater holds traces of every ocean current. A neuron in your brain might enfold the universe's entire history. This isn't just poetry. Bohm's mathematics described reality as a series of nested, hollow movements, where even time and space emerge from a timeless, flowing totality. The implications ripple into consciousness itself. Bohm speculated that thought arises from the implicate order, meaning our minds aren't isolated observers but participants in this unfolding dance. When you solve a problem creatively, it might not be linear deduction. It could be your brain unfolding a solution already latent in the deeper fabric of reality. Artists and inventors often describe inspiration striking out of nowhere. Bohm would argue it came from everywhere, a momentary glimpse into the implicate's infinite potential. Critics dismiss this as metaphysics, but modern physics keeps stumbling into Bohm-like ideas. The holographic principle, quantum field theory, even dark matter's invisible web, all hint at a universe far more interconnected than classical physics ever imagined. Whether the implicate order is literal or metaphorical, it dares us to see reality anew, not as a collection of things, but as a dynamic, unbroken whole. The next time you feel a sudden connection to a stranger or sense the pulse of the cosmos in a quiet moment, remember, you might be brushing against the hidden layer where everything is already touching. We think we know what dimensions are: up and down, left and right, forward and backward, with time ticking steadily forward. But what if these 4 dimensions are just the surface of something far deeper? String theory, one of the most ambitious frameworks in modern physics, proposes that the universe hums with hidden layers, tiny, curled-up dimensions wound so tightly they're invisible to our everyday perception. Imagine a garden hose seen from a distance. It looks like a simple line, a one-dimensional thread, but up close you realize it's a cylinder with a circular dimension wrapped around its length. Now shrink that idea down to a billionth of the size of an atom, and you've got the extra dimensions string theory suggests might be woven into the fabric of reality itself. These aren't just abstract quirks of math, they could be the hidden scaffolding connecting everything in the cosmos. In string theory, the fundamental particles we know, electrons, quarks, photons, aren't dots but tiny, vibrating loops of energy like microscopic guitar strings. And just as a guitar's pitch depends on how the string vibrates, the properties of particles might arise from how these cosmic strings resonate across multiple dimensions. Some vibrations could correspond to gravity, others to light or matter. But here's the wild part: these strings don't just wiggle in the 4 dimensions we experience. They dance through as many as 10 or 11, with the extra dimensions folded into intricate shapes called calobi. Manifolds geometric twists so complex they've been described as the DNA of the universe. Now, how could these hidden dimensions link seemingly separate phenomena? Enter brains, short for membranes. In some versions of string theory, our entire universe might be a 3-dimensional brain floating in a higher dimensional space called the bulk. Other brains could exist parallel to ours, separated by a gap in the bulk, each hosting its own universe with different physical laws. Gravity, unlike other forces, might be able to leak between brains, which could explain why it's so weak compared to electromagnetism or the nuclear forces. If gravity disperses into the bulk, what we perceive as its faint tug could be just a fraction of its true strength, like hearing a muffled voice through a thick wall. This idea opens breathtaking possibilities. If brains drift close enough in the bulk, they might occasionally collide, releasing titanic energies. Some cosmologists speculate that the Big Bang itself could have been a brain collision, a cosmic shockwave birthing our universe. Even more intriguingly, if another brain floated near ours, gravitational ripples from events there, like black hole mergers, might subtly influence our brain, leaving faint imprints in cosmic background radiation or unexplained gravity waves. But here's where it gets truly mind-bending. If extra dimensions exist, they could enable instantaneous connections that defy our 4-dimensional logic. Quantum entanglement, where particles sync faster than light, might involve strings vibrating in higher dimensions, bypassing our usual constraints. A particle here and its entangled partner light years away could be inches apart in a hidden 5th dimension, like 2 ants on opposite sides of a folded sheet of paper, unaware they're actually close when the paper is flattened. The challenge, of course, is proof. Extra dimensions are too small to detect directly with current technology, but physicists hunt for indirect clues. Particle colliders like the Large Hadron Collider might find evidence in missing energy signatures of particles momentarily vanishing into higher dimensions. Or gravity might behave oddly at microscopic scales, deviating from Newton's predictions in ways that reveal hidden geometric folds. Whether these dimensions exist or not, the idea reshapes how we see reality. The universe might not just be stranger than we imagine. It could be stranger than we can imagine, with layers upon layers of hidden geometry whispering just beyond our perception. The next time you gaze at the stars, consider this. What looks like empty space might be a bustling intersection of unseen dimensions, where every particle is a note in a cosmic symphony played across 11 strings. The universe breathes, not metaphorically, literally, across scales from swirling galaxies to the dance of subatomic particles. The cosmos exhibits behaviors eerily reminiscent of biological systems. Consider the cosmic web, that vast neural network of galaxies woven by dark matter filaments. Its structure mirrors the human brain's synapses with uncanny precision, suggesting nature might have a universal playbook for organizing complexity. But what if this similarity runs deeper than pattern alone? What if stars, galaxies, and black holes aren't just arranged like life, but function like it? Take star formation. In stellar nurseries, gravity pulls gas clouds together until nuclear fusion ignites a process strikingly similar to cellular mitosis, where division creates new life. Supernova then scatter heavy elements like cosmic pollinators, seeding space with ingredients for planets and ultimately biology. Even black holes, those devourers of matter, behave like regulatory organs. Their jets pump energy back into galaxies, preventing runaway star formation just as a pancreas secretes insulin to balance blood sugar. The universe doesn't just contain life, it performs life's rhythms on a grand scale. This perspective crystallizes in Lee Smolin's theory of cosmological natural selection. He proposes universes could reproduce through black holes, each collapse birthing a new cosmos with slightly tweaked physical constants. Universes fostering more black holes would survive by spawning more offspring, a cosmic version of Darwinian evolution. Our finely tuned laws, perfect for stars and life, might not be luck. They could be the result of eons of universal selection, a chain of cosmic ancestry stretching back to an original progenitor. The most tantalizing clue lies in homeostasis, the self-regulation seen in organisms from bacteria to ecosystems. Remarkably, the universe appears to self-regulate too. Dark energy's mysterious strength, driving cosmic acceleration, is fine-tuned to a precision of 1 part in 10 to the 120th power. Too strong and galaxies would tear apart before forming, too weak and gravity would crush everything back into a big crunch. This balance isn't static. Some models suggest dark energy's strength might dynamically adjust like a thermostat responding to cosmic expansion rates. Could consciousness be part of this self-regulation? Just as a body grows nerves to sense its environment, the universe might evolve observers to understand itself. Your curiosity about the stars, a physicist's equations, even the collective awe of a generation staring at eclipse, these could be the universe waking up to its own existence. Not as passive byproducts, but as active participants in a grand, self-referential loop. The night sky isn't just something we see. In this vision, it's something the cosmos sees through us. Long before telescopes revealed the cosmic web, ancient philosophers imagined the heavens singing. Pythagoras, the Greek mathematician, was among the first to propose that celestial bodies moved in harmonic ratios, their orbits producing a symphony so vast human ears couldn't perceive it, the legendary music of the spheres. While dismissed as poetic whimsy for centuries, modern physics is stumbling upon an eerie truth. The universe might indeed vibrate with hidden melodies, its grandest structures orchestrated by ratios eerily reminiscent of musical harmony. Take the spiral arms of galaxies, those vast arcs of stars winding through the darkness. Their spacing follows the Fibonacci sequence, the same mathematical pattern found in seashells, flower petals, and the crescendos of classical symphonies. Zoom in further, and quantum physicists discover that subatomic particles resonate at precise frequencies, like microscopic tuning forks. Even the cosmic microwave background, the afterglow of the Big Bang, pulses with slight variations that, when converted to sound waves, produce a haunting hum, a bass note ringing through space since the dawn of time. This isn't just coincidence. The equations governing wave dynamics in music and astrophysics are strikingly similar. When a violin string vibrates, it produces harmonics multiples of a fundamental frequency that create rich, layered tones. In the cosmos, galaxies clustering along filaments echo these harmonics. Gravity's pull arranges matter into dense nodes, the notes connected by thinner tendrils, the intervals, forming a kind of cosmic chord progression. The universe, it seems, composes itself. Black holes add a dramatic crescendo. When two collide, they emit gravitational waves, ripples in spacetime that scientists can translate into sound. The resulting chirps, though far below human hearing range, match musical ratios when scaled up. In 2019, researchers at MIT even mapped the waves from a black hole merger to a piano keyboard, revealing a descending minor third interval. The same melancholic progression found in everything from Beethoven's Moonlight Sonata to modern pop ballads. Perhaps most astonishing is how these vibrations might connect the cosmos. String theory posits that fundamental particles are tiny, vibrating strings, with their frequencies determining properties like mass and charge. If true, then every electron in your body hums a specific pitch, harmonizing with quasars billions of light years away. Dark matter, that invisible scaffold, could be the universe's sustained pedal tone, a deep, unchanging resonance binding everything together. Critics argue this is anthropomorphism imposing human aesthetics on indifferent physics. Yet the math persists. The golden ratio, a proportion revered by artists and architects, appears in galaxy rotations and planetary orbits. Quantum energy levels follow harmonic progressions akin to musical scales. Even time itself might be granular, ticking in discrete Planck-length intervals like a metronome keeping cosmic rhythm. So the next time you hear a symphony or pluck a guitar string, remember, you might be tapping into the universe's oldest language. From the smallest quark to the largest supercluster, reality doesn't just move. It sings. Imagine every atom in the universe as a tiny pixel in an infinite cosmic computer screen, not just carrying mass and charge, but processing information in a grand computational dance. This radical perspective comes from information theory, which suggests reality isn't built on matter or energy alone, but on the fundamental exchange of data. At its core, the idea is simple yet staggering. Everything, from the spin of an electron to the birth of a galaxy, might just be bits flipping in nature's ultimate hard drive. The roots of this theory trace back to physicist John Wheeler's famous phrase, "it from bit." Wheeler proposed that every particle, every force, even spacetime itself, derives its existence from the answers to yes-no questions, binary choices woven into the fabric of reality. Picture a cosmic game of 20 questions where the universe isn't just keeping score, it's generating the very objects being guessed. When you touch a table, you're not feeling solid matter but an avalanche of quantum data. A trillion interactions projecting the illusion of solidity through sheer computational density. Quantum mechanics lends startling weight to this view. Consider entanglement, where particles remain mysteriously linked across vast distances. In an information-based universe, this spooky action becomes elegantly simple. Entangled particles aren't communicating, they're accessing the same underlying data stream, like two computers reading from a shared cloud file. Even the uncertainty principle, which states we can't simultaneously know a particle's position and momentum, might reflect not a limitation of measurement, but a fundamental data compression in reality's code. The universe isn't being vague, it's rendering only what's needed, like a video game loading details as you explore. Black holes amplify this idea. When matter falls into one, conventional physics suggests it's lost forever. But quantum mechanics insists information can never disappear, a paradox that led to the holographic principle. Here, the information swallowed by a black hole isn't destroyed. It's encoded on the event horizon's surface like a cosmic QR code. Scale this up, and the entire universe might function similarly, with every event etched onto a distant boundary we can't perceive. A cosmic RAM where past, present, and future exist simultaneously as retrievable data. The interconnectedness runs deeper. In quantum field theory, even empty space crackles with virtual particles popping in and out of existence, a phenomenon called vacuum fluctuation. This isn't random noise, it's the universe's background processing, a constant exchange of information that undergirds reality. Experiments with Casimir plates, which measure the subtle pressure between them caused by these fluctuations, hint at this hidden data layer. Like feeling the hum of a server room through vibrations in the floor, we're detecting the universe's computational hum. What does this mean for us? If information is primal, then consciousness, the phenomenon of experiencing and processing information, might not be an accident. Your thoughts could be localized expressions of the universe's self-awareness, nodes in a cosmic neural network. When you learn, create, or even daydream, you're not just observing reality, you're participating in its ongoing computation. The night sky isn't just a static image, it's a dynamic readout, a cosmic dashboard displaying the universe's real-time processing. Skeptics argue this reduces existence to sterile data, stripping away the richness of experience. Yet proponents counter that information isn't abstract, it's the very medium of meaning. A Beethoven symphony is at one level just vibrating air molecules. But arranged with intent, those vibrations become transcendent art. Similarly, the universe's data might not be cold numbers. It could be the language of meaning itself, a code that breathes fire into equations and spins stardust into stories. So the next time you forget your keys or solve a complex problem, consider this. You're not just a player in the universe's game. You're part of its operating system, a living subroutine in nature's endless algorithm. The connections you feel to people, to ideas, even to distant stars might not be poetic coincidence. They could be threads in reality's deepest structure, resonating with the quiet truth that nothing and no one is ever truly separate. From the swirling arms of a distant galaxy to the whirlpool in your coffee cup, nature adores a spiral. This isn't just aesthetic coincidence, it's a whisper of something deeper, a signature of universal design etched across scales so vast and tiny they defy intuition. The self-similar universe theory suggests these repeating patterns, called fractals, aren't decorative flourishes but fundamental blueprints, hinting that reality operates like a kaleidoscope where every turn reveals the same shapes, just at different magnifications. Take the humble Fibonacci spiral seen in the curl of a nautilus shell. Zoom out and you'll find the same curve in hurricane satellite images, their clouds winding inward like liquid clockwork. Pull back further and spiral galaxies like the Whirlpool Galaxy echo the design, their stars tracing arms that could be sketches from a storm chaser's notebook. Even the jets spewing from young stars twist into helical shapes, as if some unseen hand stamped the same template across light years. But here's where it gets uncanny: descend to the quantum realm, and superfluid helium, chilled near absolute zero, forms vortices that spin in perfect mimicry of their cosmic counterparts. How can a galaxy and a subatomic whirlpool share geometry? The answer might lie in the language of turbulence, the mathematics governing how energy flows through systems, whether they're made of air, water, or space-time itself. Vortices aren't the only fractal diplomats. Lightning forks across the sky in jagged branches that mirror the veins in a maple leaf, both following the path of least resistance, optimizing for efficiency. The branching patterns of lung capillaries mirror the delta of a river, both designed to maximize surface area. Even the clustering of galaxies in the cosmic web mirrors the neural pathways in your brain, with dense nodes linked by delicate filaments. Scientists quantify these resemblances using power laws, mathematical relationships that describe how properties like size, frequency, or connectivity scale across orders of magnitude. When the same equation describes the distribution of internet routers and galactic superclusters, it's hard to dismiss as mere coincidence. Diving deeper, quantum foam, the seething foundation of spacetime at Planck scales, displays bubbling textures that, when modeled, resemble the large-scale structure of the universe. It's as if the cosmos is a hall of mirrors where every reflection, no matter how small or vast, contains the same essential shapes. String theory amplifies this notion, proposing that the vibrational modes of tiny strings could generate every particle and force, like musical notes arising from a single instrument's harmonics. The universe might not just contain patterns, it might be patterns, a symphony of self-repeating geometry where the distinction between part and whole melts away. This fractal harmony raises profound questions about connection. If a quark's behavior echoes a star's, could they be entangled not just metaphorically but mathematically, even physically? Some researchers speculate that hidden conservation laws deeper than those we've discovered might govern these universal resemblances. Others propose that self-similarity arises because nature reuses solutions. The same equations that optimize fluid flow also optimize starlight's journey through dust clouds. But the most radical interpretation, that the universe is a hologram with every region containing encoded information about the whole, like a single leaf's DNA holding the blueprint for the entire tree. Whether through math, physics, or metaphysics, the self-similar universe whispers a tantalizing secret. That separation might be an illusion. The spiral of a seashell, the spin of an electron, and the swirl of a galaxy could all be verses in the same cosmic poem, written in a language where scale is just another stanza. The next time you stir cream into coffee, watch the whirlpool form, and remember, you might be gazing at a miniature cosmos, its tiny vortex a silent nod to the grand design. From quantum entanglement whispering across galaxies to cosmic strings threading dimensions we can't perceive, from the holographic dance of information at black hole horizons to the eerie resonance between brain cells and galaxy clusters, the theories we've explored tonight paint a universe far stranger, far more connected than our everyday senses suggest. Each framework, whether rooted in cutting-edge physics or ancient intuition, chips away at the illusion of separation, revealing a cosmos where distance might be a trick of perspective, where every particle could be a note in a grand symphony we're only beginning to hear. Consider the implications. If entanglement links particles instantaneously across space, if the holographic principle encodes our 3D reality on a distant 2D surface, if dark matter's filaments hum with unseen communication, then the cosmos isn't a collection of isolated objects. It's a dynamic tapestry, a living network where supernova might subtly influence the spin of electrons in your body, where your observation of a star could, in some small way, ripple through the quantum substrate binding all things. Even time, that relentless arrow, might be a foldable layer in a block universe where past, present, and future exist simultaneously, forever entwined. Yet the most humbling revelation isn't just the scale of these connections, it's how they redefine our place within them. We're not passive spectators gazing at a cold, indifferent universe. We're active participants, our consciousness perhaps a localized expression of a cosmos waking up to itself. The neural networks in your brain don't just resemble the cosmic web. In a very real sense, they might be its microscopic echo, a fractal reaffirmation that the universe loves to repeat its favorite patterns. So here's the question that lingers as we stare into the night sky. If the boundaries between you and the universe are more porous than we ever imagined, what does that mean for how we live, how we connect, how we steward this fragile planet? Are we cosmic orphans, or are we the universe's way of reaching back into itself, a thread in the tapestry beginning to recognize its own weave? The theories are many, the mysteries deep, but one thing feels certain: the more we learn, the more the cosmos whispers back that nothing and no one is truly alone. Now we turn it over to you. Which of these hidden connections resonates most? The quantum threads of entanglement, the holographic whispers of black holes, the fractal echoes between neurons and galaxies? Drop your thoughts below, because in a universe this interconnected, every perspective might just be a piece of the puzzle.